Okay, students. I'll start from the program partitioning and scheduling once again. Okay, so the size of the parts or pieces of a program that can be considered for parallel execution can vary. What is the meaning of this? When we want to execute, now it is okay, right? Is it okay, student? Okay. So when we want to execute the instructions parallelly, what we will do? We will have different threads, right? During parallel programming, we will assign some different tasks to different threads, right? So what we will do? We will partition entire program into a pieces, right? So now each piece will have, it is not that always it should have same number of instruction in each set or in each piece. It is not like that, right? So that number of instructions in each set or each piece may vary. So that is nothing but granular size or granularity or granule size. Okay, so number of instructions in each piece or each module or each program segment, we will call it as granule size or granularity. Okay, so that they're dividing the programs into different pieces, we will call it as program partitioning. Why it is required? In order to execute the program parallelly. Okay, so that we can give each piece into a different threads. Okay, I hope this concept is clear. So now we can have three different categories here: fine grain, medium grain, or coarse grain. So it is based on, this classification is based on number of instructions in each piece. Okay, so we can have fine grain, medium grain, or coarse grain. Okay, so we will see later what is the difference. Okay, fine grain means it will have less number of instructions. Medium is this more than a fine grain and less than coarse grain. Coarse grain means we will have millions of instructions. We will have millions of instructions in each piece. Okay, so based on the number of instructions, we will divide this into grain sizes into fine grain, medium grain, or coarse grain. Okay, I hope it is clear. Now let's latency. What is latency? Latency is nothing but time required for any task. Okay, latency is nothing but time required for doing the things. So now we can have two types of latencies here. We know that when we are executing the things parallelly, the each subunit or subsystem, or we can say processor, it can, okay, they want to communicate with each other, right, in order to share the resources or share the data. So that time, in order to communicate with each other, they will spend some time, right? So that time we will call it as latency. Okay, 1 second. Okay, many are joining now. Okay, students, let me continue. Now, I can have memory latency and synchronization latency. So, memory latency is nothing but time required by a processor to access memory. So, now what happens? In between the execution of instructions, processor needs to fetch the data from the memory. It wants to access the data from the memory. So that time it will spend some amount of time. So that time we will call it as memory latency, because it wants to communicate with the memory device. So that latency we will call it as memory latency. Next one is synchronization latency. So it is the time required for two processors to synchronize their execution. So why they want to synchronize? For example, the one simple example I'll give you, students. Now I want to add n natural numbers. I want to add n natural numbers, say 1 to n. If my n is 10, then I want to add 1 to 10 natural numbers. Now, if I have two threads, if I am executing the program parallelly, then I think I have two threads. Now, what I will do? I will divide that whatever the for loop is there, inside for loop I will add, right? So whatever the for loops are there, whatever the instructions means 10 iterations will be there, right? Because my n is 10 now. So what I will do is I will give 5 iterations to one process thread, and another 5 instruction iterations means it is instruction only to one more thread, right? So that time what happens, whatever the result obtained by each thread is not a final result, it is partial result, right? Because first thread will add 1 to 5 and it will obtain the result, and second thread will, it is not that in order it is always, or it can add random numbers also in between, means of 1 3 7 9 or 10, like that also it can happen. So, but whatever the result they will get, it is not a final result. So, after getting the partial result, it wants to add those two results. So, that time what happens? They will synchronize each with each other in order to share that result and to merge that result. So, this is a simple example I have given. So, like that, we can have in complicated programs, we can have every now and then a processor wants to synchronize with each other, so that latency, whatever the time they will spend in order, it is not it is also a part of execution, but it is not, they are not spending time for execution rather than spending on communicating with each other. Okay, so that is nothing but synchronization latency. I hope you have got now what is latency. First, it is time required for communication between different subsystems. So we can have memory latency or and synchronization latency. So now, actually, this computational granularity. What is computational granularity? Granularity is nothing but size of a program, means number of instructions in a program, and communication latency are closely related. Okay, because in order to reduce the latency, we need to do some changes in the granularity also, so they are interrelated things: communication, computational granularity and communication latency. Okay, students, I hope you have understood what is program partitioning and what is grain size and what are the three different grain sizes, we can describe grain size using three different things, that is fine grain, coarse grain and medium grain. Okay, now based on the grain size, we can divide this parallelism into 5 different levels. We can divide this into 5 different levels. That is, first I'll start from the bottom. So first one is instructions or statements. Okay, we can have instructions, simple instructions, or we can have simple statements. Okay, then above that we have non-recursive loops or unfolded iterations. Non-recursive loops. Okay, it is not recursive. Recursive, you know that it will call itself. Okay, that that is recursive loop. If we have any simple loops which is not non-recursive or unfolded iterations, okay, that is the second level. Okay, above that we can have procedures, subroutines, tasks, or coroutines. Okay, procedure is nothing but in your microprocessor programming you have seen. Okay, small procedures you will write. Okay, using PROC, that reserved word you will use for that. So, or subroutine. Subroutine means sometimes we will use branch statements, jump statements. Okay, so one subroutine we will have and we will jump there. So that is nothing but subroutine. It is set of instructions, and above that we can have subprograms, job steps, or related parts of a program. So if you see, as I go to upper level, the number of instructions will be increased. Okay, when I go from bottom to, when I go from bottom to up, then number of instructions in each level will increase. Okay, that is why if you see in right hand side we have, one second students, what happened? Okay, so if you see in right hand side we have fine grain, medium grain and coarse grain. So last two, the bottom two levels comes under fine grain because we have instructions or statements or non-recursive loops. We know that number of instructions in this level will be less. Okay, so it comes under fine grain. So this procedures or subprograms will come under medium grain, means more than this whatever the number of instructions, limited number of instructions are there for fine grain. The in this third and fourth level it will be higher than that. Okay, so that is why we will categorize into medium grain. Then sometimes this subprograms can have more than the number of instructions as that of medium grain also. So that time if it has more than that, we can categorize into coarse grain also, means sometimes it fall into coarse grain category. So then if you see in left hand side from up to bottom, one arrow mark is there. Okay, so higher to lower level, what it tells is increasing communication demand and scheduling overhead. As you come down, it will increase the communication demand and scheduling overhead. Why it increases the communication demand, students? If we have less number of, if we include less number of instructions in each set or each piece, then automatically we will have more number of partitions. Yes or no? If I have 100 if I have 100 instruction in my program, for example, if I, then I will divide it into fine grain fine grains, then I will have more number of grains, right? Or more number of partitions I will have. If suppose I am including only 10 instructions, then I will have 10 grains. That is fine grains because the number of instruction in each grain is less. It is 10. Okay. So now if I include 50 instruction, then number of grains will be less. Only 2 grains I will have, or 2 partitions I will have. But size is more, right? Size of each grain is more. So it uh, so we got only 2 partitions. So what they are telling is, as the finer the size of the grain, more the or increasing communication demand, because we will have more partitions, so each wants to communicate with each other, so latency will increase. Yes or no, students? Okay, as the finer the size of grain, more the communication demand and scheduling overhead. Okay, and as the finer the size of grain, higher degree of parallelism. If we have less number of instructions, then degree of parallelism will be more, because if I have 10 partitions with each partition is having 10 instructions, then I can execute 10 pieces parallelly, so that within this one if I can tell, if one machine cycle is of 1 second, then within 1 second only I can execute, right? Because parallelly I'm doing the things. 10 partitions are also getting executed parallelly. But if I have only 2 partitions, then parallelism, degree of parallelism is less, right? Because only in each partition, only 2 threads can execute those partitions, and each will have more number of instructions. So that time we cannot obtain higher degree of parallelism. Getting, students, now? So as the finer the grain of size of the grain, we will have high degree of parallelism. At the same time, we will have more increasing communication latency also. That is the disadvantage. But degree of parallelism will be high. Got, students? So this is a brief description of levels of parallelism. Now, we will see one by one now. Each level we'll see one by one. Okay, first we will see instruction level parallelism. Each level we are going to see what is the number of instructions we can include, okay, and what are the advantages. Now, in instruction level parallelism, as it is fine grained, we can have only less than 20 instructions. We can have only less than 20 instructions in each grain. Okay, so number of candidates for parallel execution varies from 2 to thousands with about 5 instructions or statements on an average. Okay, on an average we can have 5 instructions being the average level of parallelism. So here you have to remember, in instruction level parallelism we can have less than 20 instructions per grain. So what is the advantage? There are usually many candidates for parallel execution. Candidates here are nothing but threads. Okay, here are threads. Okay, so for parallel execution, compilers can usually do a reasonable job of finding this parallelism. It is easy to detect also. This level of parallelism is easy to detect, and we can have more partitions with less number of instructions, which will lead into higher degree of parallelism. Okay, so this is what about instruction level parallelism. In bottom level we have instruction or statement parallelism, that one. Next is loop level parallelism. So in loop level parallelism we can have less than 500 instructions, less than 500. See students, in first we can have maximum is 20. In this level, maximum is 500 instructions. So if we have more than 20 and less than 500, that grain will fall under this loop level parallelism. Okay, loop level parallel, but still it is fine grain only. As in, by this figure, you can understand that this loop parallelism also comes under fine grain. Okay, but under fine grain we can have two levels of parallelism. That's it. Okay, so now if a loop operation is independent between iterations, it can be handled by a pipeline or by a SIMD machines. What they are telling is, when we have a loop, inside loop we can have any number of instructions. If those operations or instructions are independent of each other, then we can uh, feed that into pipeline, means parallelly we can, concurrently we can execute, or SIMD, single instruction multiple data. So that because in loop you know that instruction is same, we are adding, but the data will change in each iteration, right students? Because we will, in a loop, index also will change. I will be 1, then I becomes 2, like that it goes, right? So data will change, will vary, but the instruction whatever you are executing inside the loop will be same. Okay, throughout the loop execution. So what they are telling is, if it is independent of each other, we can go for pipeline or SIMD machine. Okay, so next, most optimized program construct to execute on a parallel or vector machine. So if we optimize, you know students, means we are reducing the number of instructions such that it should not, or it should retain the original meaning. It should not change the meaning of that, whatever the for whatever the purpose it has created, it should not change that. Okay, but we are reducing the, in the compiler design we have seen that. Okay, what is optimization? Okay, with the example we have seen. So some loops are difficult to handle. If we have recursive loops, it is difficult to handle, so that time it will not fall into loop level parallelism. It is in loop level, it is non-recursive, we have seen. So loop level parallelism is still considered fine grained computation. So loop level parallelism will have less than 500 instructions, so it will fall into fine grain category. Okay, so next is procedure level parallelism. So in procedure level parallelism, we can have less than 2000 instructions. Okay, and it is of medium sized grain. Okay students, so now what you have understood, if we have 0 to 500, if we have 0 to 500 instructions, it is nothing but fine grain. It is fine grain, right? So but in again, if we have less than 20 instruction, it comes under which level? Instruction level parallelism. If we have more than 20 instructions and less than 500, it comes under loop level parallelism. So now fine grain is done. We are talking about coarse grain now. Sorry, medium grain now. So in medium grain, we can have less than 2000 instructions. So detection of parallelism is more difficult here. As the number of instructions are more, the detection of parallelism. Detection means what? Finding out the parallelism, where we can give the instructions for parallel execution, because we need to take care of dependencies, right? If we have any dependency among the instructions, we cannot go for parallelism. So finding out that parallelism is difficult here, because we have more number of instruction. But in case of fine grain, it is easy to find out the parallelism, because we will have less number of instructions. Okay, so communication requirement less than instruction level. So here communication, one advantage is like detection of parallelism is difficult. So by default degree of parallelism is also will be less. Okay, but communication requirement less than instruction level, because we will have less number of threads here, right? Less number of partitions. So communication requirement will be less. Okay, so SPMD, single procedure multiple data, is a special case here. Okay, single procedure multiple data, it is like your single instruction multiple data only, but it is single instruction means only one instruction. If we have procedure, we know that in procedure we will have some number of instructions. Okay, that is less than 2000 instruction. So multitasking belongs to this level. So if we want to do the multitasking programming, then we will go for this level. Okay, multitasking. So subprogram level parallelism. So here it is also called as job step level. So grain typically has thousands of instructions, medium or coarse grain level. So here we cannot tell that whether it comes under medium grain or coarse grain. It is based on the number of instructions. So they have told that we can have thousands of instructions. If it is less than 2000, we can tell that it is medium. If it goes beyond the 2000, it is coarse grain. Got students? So it can fall either into medium grain or coarse grain. Okay, if we have less than 2000, we can tell it is medium grain, otherwise it is coarse grain. Okay, job steps can overlap across different jobs. Okay, so here multi-programming conducted at this level. So whereas in procedure level, multitasking belongs to procedure level, multi-programming belongs to subprogram level parallelism. You know, in operating system you have studied what is multi-programming, what is multitasking, right? So no compilers available to exploit medium or coarse grain parallelism at present. So we don't have any supporting compiler for this type of parallelism. So no compilers available to exploit medium or coarse grain parallelism. Okay. So next is job or program level. So program means entire program. So we will have more number of instructions here. So corresponds to execution of essentially independent jobs or programs on a parallel computer. Okay. So this is practical for a machine with a small number of powerful processors, but impractical for a machine with a large number of simple processors. What they are telling is, when we are executing an entire program at a time, then we need to have a single processor with the higher the performance capacity. Okay, but if we have many number of processors and with less capacity, then it is of no use, because we cannot detect the parallelism also in this type of in this level of parallelism. So we cannot go for parallelism. So what is the use of having n number of processors with less capacity? Instead of that, we can have one processor with higher capacity. Got students? One processor with higher capacity. So this is practical for a machine with a small number of powerful processors, but impractical for a machine with a large number of simple processors. Simple means less capacity. Okay. So next is communication latency. So balancing granularity and latency can yield better performance. So what they are telling is, as we know that if we do the if we divide the program into finer parts, then there will be a more communication latency, right? But the degree of parallelism will be more. So what they are telling is, if we try to balance the brain size and latency, then we can yield a better performance. Okay, so various latencies attributed to machine architecture, technology, and communication patterns used. Okay, it is actually based on this, latency is based on the machine architecture, because which type of network we are using in order to communicate, which type of which technology we are using. Okay, and communication patterns. Okay, that is nothing but again network. So that will be affected, that will be affected. Okay, so latency imposes a limiting factor on machine scalability. So what is scalability? Scalability is means adding the number of more number of devices into a existing system, right? So latency imposes a limiting factor on machine scalability. So if latency is more, we cannot go for adding the more number of units, because again if we have more number of units, again we need to communicate with each unit, so that latency will be high. So memory latency increases as memory capacity increases. One more thing is, when we increase the memory capacity, that time memory latency also increases. Okay, memory latency also increases, because if we have larger memory, then it will be difficult to fetch the data from the memory, or it difficult to access, so latency will be more. So this is like one interrelated with each other, granularity and communication latency. So we have to take it, we have to balance. Okay, we have to balance so that we can yield a better performance. So limiting the amount of memory that can be used with a given tolerance for communication latency. It is not that, see students, what I want to convey is, if we think about faster or less execution time, okay, fastest system, then it is not that always we need to have a large memory. Okay, it is that is what they are telling. If we have a large memory, then there will be a more late communication latency also, or memory latency also. Okay, so all the things we need to take care. Next, inter-processor communication latency. So here needs to be minimized by system designers. So who can take care of this inter-processor communication latency is system designer. Okay, while designing the system only, they have to see that there will be a less latency, inter-processor communication latency. So affected by signal delays and communication patterns. Once again, one second, students. Am I audible, students, now?
Yes, ma'am.
Okay. So, so what they are telling is, the interprocessor communication latency will be affected by signal delays. You know that in order to communicate, we will use some signals, or we will use some communication patterns. It can be mesh topology or bus topology. So different types of network topologies or patterns we will use, right? So it will that latency will be affected by both signal delays as well as communication patterns. Some patterns will have less or it will take less amount of time in order to communicate. Okay, it is based on the pattern, communication pattern. So generally we can tell that, so n communicating tasks may require, task means your processors require n into n minus 1 divided by 2 communication links, and the complexity grows quadratically, effectively limiting the number of processors in the system. So generally we can tell that if we have n processors or n tasks, then we will have n into n minus 1 divided by 2 communication links. So, okay, this is general calculation. Okay. So next, what type of communication patterns we can have? So determined by algorithms used and architectures support provided. So how we will determine which communication pattern we want to use? So that will be determined by algorithms used, which type of algorithm we are going to use, and architectural support. Again, hardware support. Okay, so you should remember always that whenever we want to do some enhancement in a compiler or software, we need to take care of hardware also. Same thing, it is vice versa. If we want to do some development in hardware, then we have to see that whether that will be supported by our compiler or system. Okay, so both that, it is vice versa, both we need to balance. Okay, so then patterns include permutations, broadcast, multicast, and conference. Okay, so these are different types of communication patterns. Okay, so this you have seen in networks, right? So what is broadcast, what is multicast, what is conference? Okay, so trade-offs often exist between granularity of parallelism, communication demand. Again, it is function of both this granularity of parallelism and communication demand. Okay, so next is, are you understanding, students? Is there any doubts in this program partitioning and grain size and different levels of parallelism? Is there any doubt? Yes, students, I want response. Can I continue?
Yes, ma'am.
Okay. Next, we will see what is grain packing and scheduling. Now, we will divide the program into subprograms or partitions. So then we have to pack those grains, because in order to reduce the latents. Okay, if we put all the grains in one module, okay, or we will set those grains or different partitions, then there will be a less number of interprocessor communication, because we are putting all together. Okay, we are packing. So how it happens, we will see. So before doing that, we will get two questions always: how to partition, or how can I partition a program into parallel pieces to yield the shortest execution times? That is one question. And what is the optimal size of parallel grains? So two questions comes in our mind when we want to partition the program. So these things we have to find out the answer for that first. Okay, so how can I partition program into parallel pieces? In order to get the what is the final objective, we need to get the shortest execution time, right? We need to get the shortest execution time. That is our motto, that is our objective. So what will be the and we know that if we have when we have a large number of instructions, what is the disadvantage? When we have less number of instructions, what is the disadvantage or advantage? Both we have seen. So we have to balance those things. So there is an obvious trade-off between the time spent scheduling and synchronizing parallel grains and the speed up obtained by the parallel execution. So again, there is a relationship between time spent scheduling. Now, what is scheduling, students? First, I will divide the program into different partitions. Then I have to schedule that. Means after this instruction, instruction will get executed. Order of execution. Scheduling is nothing but order of execution. So that we are going to see in next slide. So what they are telling is there is a trade-off between the time spent scheduling and synchronizing parallel grains. Okay, synchronization means communicating with each other, and the speed up obtained by parallel execution. Okay, so all the things are related here. So one approach to the problem is called grain packing. So in order to avoid this, in order to avoid the more number of interprocessor communications, we will do the grain packing. We will put all together. Some a number of grains we will put together, and we will call it as one unit. got students. That time interprocessor communication will be less because it fall into one. It comes under one unit. Entire unit we will consider as one subunit or functional unit, right? So that time we can reduce the latency, because we have seen that in order to get the higher degree of parallelism we need to divide it to finer partitions, right? We need to have the fine grains, but same time it will increase the communication latency. That is the disadvantage, right? Our objective is to get the higher degree of parallelism, but to overcome that latency disadvantage or drawback, what we will do, we will pack the grain together so that we will decrease the communication latency. So that is the solution. In order to decrease the communication latency, we can go for grain packing. Grain packing, we will see how it happens. So before that, so how we will represent that using program graphs and okay, using program graphs, we will represent how this program is divided into different partitions and how this each partition is packed together. In order to understand that, we will have one program graph. So first we will see the notations in that graph. So we will have two numbers within parentheses. We will have two numbers where first number, that is n, is nothing but node name. What is the name of that node? Okay, and second number, that is s, will denote the size, will denote the size. So larger s is equal larger grain size. That we know that the if we have n number of instruction, then n is the size of that grain. So if larger the number, larger the grain size, right? So then edges in a program graph, we will have edges. And now first we whatever we have discussed is about nodes. Okay, so now edges will also have two values within parentheses. First one is variable being communicated, through which variable we are communicating, because when we want to communicate with each other, then why we will communicate, either we want to get the value for some particular variable. Okay, if we want to communicate with the memory also, what we will do, we will fetch some data from the memory and put in one variable. So it is through variable only. It is through message passing or variable, right? So edges is equal to v comma d. So v is nothing but variable being communicated. So d is nothing but delay. Communication delay. So four things we are going to represent here. Within node also, inside the node we will write two things, that is name of the node and size of the grain, and on the edges we will write v and d. V is nothing but variable being communicated, d is nothing but what is the delay, in order to communicate with each other. Okay, so packing two nodes produces a node with the larger grain size and possibly more edges to other nodes. Okay, so with the example, we'll see that time will understand. So packing is done to eliminate unnecessary communication delays or reduce overall scheduling overhead. That was one of the advantage of fine grain systems. So in order to overcome that, we are introducing grain packing. Okay, so whether this program is visible, graph is visible properly. Is it visible, students?
Yes, ma'am.
Okay, so now whatever the left hand side graph is there, I'll explain that. Now you forget about whatever the shapes are there. See, students, A, B, C, D, E is there. You forget about that. You think that each node is one grain. Okay, each node is one grain. Okay, so you don't consider that one whatever the packings are there, no, A, B, C. You don't consider that now. Beginning at the initial stage, we have some nodes here with the name of the node and the size of the node, and we have edges. On the edges we have written through which variable we are communicating with each other and what is the uh, delay, right? So when if see, students, now I have 1 comma 1, So what is the meaning of that? Anyone can tell? Inside first node, I have 1 comma 1. So what is the meaning of that, students? Can anyone tell? What is 1 comma 1? So it is nothing but name of the node. So name of the node, I have given it as 1. Okay. So what is one more 1 indicates? It is size of the grain. Means 1. 1 means I have one instruction in that grain. I have one instruction in that grain. Okay. So now 2 comma 1, same thing. Number name of the node is 2. I have one instruction in that. Third one, name of the instruction is 3, one instruction. Then 4, 1, 5, 1, 6, 1. Then 7, 2 is there. What is the meaning of that? I have two instructions in seventh node. I have two instructions in eighth node. I have two instructions in ninth node. Like that it goes. Okay. Up to 17 nodes I have, and from 7th to 17 nodes, 17th node, I have two instructions. Means size of that node, those nodes are 2. Okay. So now what happens here? If we see the edges, on each edge we have a comma 6, from 1 to 1 to 7 to 2. If you see, I am communicating through variable called a, and delay is 6. That 6 can be some nanoseconds, microseconds, whatever. Okay. So it is 6. Okay. So then from 2 to 2 comma 1 to 7 comma 2, I have C students. When you see this diagram, what you will understand, there is a flow, dependence graph it is. Okay. If you don't consider that those A, B, C, D packings, if you only consider nodes and these edges, then it looks like your dependence graph, right? It looks like your dependence graph with extra notations. That is communication latency and through which variable we are communicating. Otherwise, just we will have arrow mark, right, students? So we can say that there is a flow dependency. There is a flow dependence. When we have arrow mark, we can tell that there is a flow dependency. Okay. So I can tell that after executing first and second node, see students, here node is nothing but one operation. What students? Node is nothing but one operation. So one first and second, after executing first and second node, only I can execute seventh node. So here also, if you see, after executing third and fourth node only, I can execute eighth. And again, after executing, yeah, after getting the value of fourth node, whatever the variable is there in fourth node, only I can execute 8th and 11th also. Okay. So like that it goes. There is a dependence. It also shows the dependence among the nodes. Okay. Dependencies among the nodes. So if you see the edges, you will understand. Okay. So which through which variable it is being communicated, and what is the delay. Okay, so now if you see this students, what you will understand here, many number of interprocessor communication is there, and if you calculate the delay also, it will be more. It will be more, right? So in order to avoid that, we are going for grain packing. So how I can pack? What I will do is here, I will first check in order to pack, I want to check the dependence. I need to check the dependency. Okay, if there is any dependency among the instructions, so I cannot pack it together. Okay, if there is no dependency, then I can pack it together. Okay, I can execute parallelly. So now see students, 1 comma 1, 2 comma 1, 3 comma 1, 4, 5, 6, 11 are packed together. Why because if you uh, see other whatever the packings are there, there is a dependency. So here I can one first node I can execute at a time with the second node. Okay, third, because among this first, second, third, fourth, fifth, there is no dependency. God students, there is no depend. So I am I have packed together. So here 7 to 8 to I have packed, because after getting this, after executing this eighth one grain, whatever the pack is there, after that only I can go for B and C. So I have packed it differently. Okay, in this 7 2 and 8 2 I have packed and named it as B. Okay, 9 2 and 10 2 I have packed and named it as C. Okay, same way here D, E I have packed. Okay, so that there will be a less number of communications. Okay, there will be a less number of interprocessor communications, so that I can reduce the latency also. So if you see the right hand side diagram, it is, see students, first diagram, what is that? Fine grain program graph. Okay, that is why I told don't consider that packing here before. Okay, now I have packed, and this that became coarse grain now, because uh, whatever the number of instructions are there in each this one grain is increased now, right? So a comma 8 total size is 8. Okay, so then I have written all the delays here. Otherwise it is 6 means 4 times 6 means 24. Now only 6 it will use, because at a time I can communicate with B. Got students now? At a time I can communicate with B with the 6 as a latency. So I can reduce the latency, because I'm treating it as whatever the 7 nodes are there here, 1 to 6 and 11. I am taking it, considering it as one unit. So there is no, actually, we can reduce the number of communications. Okay, number of communications, so that I can reduce the delay also. So same thing for all the grains. Okay, so I hope you have understood this. What is grain packing? Okay, the main objective of grain packing is to reduce the latency. That's it. Communication latency. Next is scheduling. Okay, next is scheduling. Now, a schedule is a mapping of nodes to processors and start times such that communication delay requirements are observed and no two nodes are executing on the same processor at the same time. So it is mapping of nodes to processor, means I am giving the instruction or node some operation to particular processor. Scheduling. So I am giving the order of execution. I'm telling that which instruction will be executed by which processor and what is the order. Okay, that is nothing but scheduling. About students. Okay, so some general scheduling goals are: schedule all fine grain activities in a node to the same processor to minimize communication delays. So what they are telling is, all fine grain activities in a node to the same processor. We have to give everything to the same processor, so that we can reduce the communication delays. If we are executing it in one processor, then there is no need of synchronizing with another process, because all the data, whatever the result it gets, will have it, the same processor will have within that. Okay, so there is no need of synchronization. You have seen, students, what is synchronization with the one example. While calculating the this one, we have seen, right, with the program flow graph, uh, how many machine cycles it will utilize. Okay, that is hardware parallelism and software parallelism mismatch. That time I have told that synchronization, right? We have inserted synchronization instructions. Okay, so if we are having all the data within the same processor, then there is no need of synchronizing with another processor. So they are telling that you put all the fine grain instructions to the same processor, means map to the same processor, so that single processor will execute all the fine grain instructions. Okay, so some one second one is select grain sizes for packing to achieve better schedules for a particular parallel machines. So we have to select the grain sizes for packing to achieve the better schedules. While packing also, I have told that in order to reduce the communication latency, I am packing the nodes. While packing, we have to take care that it has to achieve the better schedules. Okay, for a parallel machines. Other, there is no use of packing the nodes. Okay. The next is node duplications. This topic I'll continue in the next class, students. One example is there. If I start that, so this is, yeah, in next class I will do, okay, node duplication. From node duplication, we continue in the next class. Any doubts, students?